So good morning, everybody, and welcome. It's good to see you all. I'm Brian Greene, co-founder of the World Science Festival with Tracy Day. Wow, rowdy crowd for 8 o'clock in the morning. That is a very, very good sign. So we are so pleased that you could join us for this announcement of the Kavli Prizes, which recognizes scientists for their seminal advances in 3 research areas: astrophysics, nanoscience, and also neuroscience. The recipients, as I think many of you know, are chosen every 2 years by a committee of distinguished international scientists, some of whom we will meet in just a little while. The Kavli Prize is a partnership between the Norwegian Academy of Science and Letters, the Kavli Foundation, and the Norwegian Ministry of Education and Research. Before we get to the program, I would like to just spend a quick moment thanking our extraordinarily generous sponsors and donors who completely make the World Science Festival possible and have done so since the very beginning of the festival itself. And they include our founding benefactors, the Simons Foundation, the Alfred P. Sloan Foundation, and the John Templeton Foundation. This year's major supporters are Ann Ziff, the Bezos Family Foundation, Con Edison, the Della Pietra Family Foundation, the Kavli Prize, and New York University, where, of course, we are here now, and we are deeply grateful to NYU, and in particular to President Andrew Hamilton, Lynn Brown, Paul Horn, Catherine Fleming, and, of course, the terrific team at the Kimmel Operations for helping us make today's event possible in this wonderful space. So please join me in thanking all of those. I'd also like to extend a special welcome to a few people in the room with us today. Robert Kahn, who's president and CEO of the Kavli Foundation. Øystein Hove, Secretary General of the Norwegian Academy of Science and Letters, who's not as visible as Robert Kahn, but there you are. Yes, you are just as visible. I completely take that back. Harriet Berg from the Norwegian Consul General. Maybe she's not as, am I, maybe, yeah, I really do need some glasses, I think, something of that sort. All right, excellent. So now it is a great pleasure and an honor to introduce Dr. Shirley Ann Jackson, president of the Rensselaer Polytechnic Institute since 1999, described by Time magazine as, quote, perhaps the ultimate role model for women in science, for which I will take the liberty of removing the word perhaps. Dr. Jackson has held senior leadership positions in academia, government, industry, and research. She served as co-chair of the United States President's Intelligence Advisory Board from 2014 to 2017, and as a member of the President's Council of Advisors on Science and Technology from 2009 to 2014. Before taking the helm at Rensselaer, Dr. Jackson was chairman of the U.S. Nuclear Regulatory Commission from 1995 to 1999, and in 2016, Dr. Jackson was awarded the National Medal of Science for her work in condensed matter physics and particle physics, and for science-rooted public policy achievements. Dr. Jackson holds an SB in physics and a Ph.D. in theoretical elementary particle physics, both from the Massachusetts Institute of Technology. Please join me in making a warm welcome to Dr. Shirley Ann Jackson.
Professor Greene. I'm delighted and honored to be here. This is my second appearance at the World Science Festival. I was here at the beginning, but especially honored to have the privilege of offering to this distinguished gathering a few thoughts about scientific progress in advance of the announcement of the Kavli Prizes. And such prizes, which celebrate fundamental discoveries and the scientists who drive them, are truly important. They are especially essential now when in the United States and in some other nations there seems to be a waning appreciation for all that discovery science does to elevate our knowledge of our world and the universe and to improve lives on a grand scale. Now, certainly, there has been a waning public investment in research and development in the United States as a share of the federal budget, a decline from over 10% of the federal budget in the mid-1960s to under 3% in 2017. There also is a worrisome skepticism among the general public about the work that we scientists do, particularly in fields such as climate change. Tellingly, an ongoing survey found that a majority of Americans now believe that although it has many benefits, that science is changing the nature of human life too quickly. But meanwhile, other nations are investing vigorously in scientific discovery and technological innovation, especially China, whose research and development enterprise has experienced torrid growth over the last 15 years, with more to come under its newest 5-year plan, and which has now surpassed the United States in its number of peer-reviewed science and engineering publications. Now, ultimately, the long-standing dominance of scientists who are citizens of the U.S. in major awards such as the Nobel and Kavli Prizes may shrink as China focuses on groundbreaking research in fields that include brain science, quantum communications and computation, and deep space exploration. But they are not the only country making such investments. Now, we know that research is inherently collaborative across nationalities, geographies, ethnicities, genders, generations, and disciplines. Nonetheless, the decline in support for basic and applied research is especially frustrating to the community of scientists here in the U.S. because a declining national focus on research is playing against the rapidly expanding possibilities for discovery brought about by powerful tools such as CRISPR genome editing, human-induced pluripotent stem cells, petascale computing power, advanced data analytics, and leaps forward in artificial intelligence and machine learning. Now, scientific careers always have required tenacity and courage. Of course, brilliance, but tenacity and courage. And today, surely more than ever. So this morning, I would like to briefly consider the nature and value of that tenacity and courage, reflected in the different ways that great discoveries are made, and all that we gain as a nation, as a society, and as a species from these discoveries. Now, one need only look at Dr. Ray Weiss of MIT, who shared the Kavli Prize in astrophysics in 2016, and of course the Nobel Prize in Physics in 2017, for his foundational work in the detection of gravitational waves to understand one way that discoveries occur. Now, when I was an undergraduate physics major at MIT, Dr. Weiss was an assistant professor of physics there, known for his brilliance. Now, although gravitational waves, distortions in space-time, as you know, caused by the acceleration of massive objects, were postulated by Henri Poincaré in 1905 and predicted by Albert Einstein in his general theory of relativity in 2016, it was long thought that instrumentation sensitive enough to detect them directly could never be made. But then Dr. Weiss was asked to teach a class on general relativity at MIT, and in speaking with students about potential detectors for gravitational wave phenomena, a spark was lit. And he worked a long time on this. And in 1972, as I was completing my doctorate, Dr. Weiss laid out the design for a laser interferometer gravitational wave observatory, which would become the twin detectors of LIGO, and spent the next 40-plus years realizing that vision, until September 14th of 2015, when both LIGO detectors recorded the gravitational waves generated by the collision of two black holes nearly 1.3 billion light years distant. Now, Doctors Ray Weiss, Kip Thorne, and Barry Barish, as you know, were awarded the 2017 Nobel Prize in Physics for their work to detect gravitational waves. Now, because of his persistence, the persistence of his co-winners of the Nobel Prize, and that of more than 1,000 collaborators, as well as the National Science Foundation, which invested over $1 billion in LIGO, Dr. Weiss and his many collaborators have not only confirmed Einstein's prediction of gravitational waves, we have been given new information about and ways to study black holes and neutron stars. Now, beyond that, we now possess a new way, in fact, to conduct astronomy using gravitational waves rather than electromagnetic radiation, which could one day allow us to peer even further back in time, even beyond the surface of last scattering, when the universe became transparent to light, to study phase transitions in the earliest universe. Science is indeed a source of wonder. Now, of course, an unwavering and intentional focus on a fundamental question about the nature of our universe is not the only kind of tenacity that matters in science. There also is the tenacity of pursuing an explanation for puzzling phenomena that arise unexpectedly, the alertness to anomalies that do not fit the current scientific paradigm as described by Thomas Kuhn in his classic book, The Structure of Scientific Revolutions. Now, in 1978, I always feel like I'm present at the great things. I had the great pleasure to be a theoretical physicist at AT&T Bell Labs in New Jersey, when my vice president for research, Dr. Arnold Penzias, and his colleague, Dr. Robert Wilson, were awarded the Nobel Prize in Physics. In 1963, as you know, Dr. Penzias and Dr. Wilson, radio astronomers, were using a powerful radio telescope that had been built by Bell Labs to demonstrate the feasibility of communication satellites. Now, when the first satellite for television transmission, Telstar, had its transistors ruined by high-altitude nuclear tests, Doctors Penzias and Wilson were then free to use the telescope for their own investigations. Now, attempting to detect a halo of gas surrounding the Milky Way, they found that the sky was too bright in microwave radiation for the halo to be detected, and everywhere they looked, space was slightly warmer in temperature than it should have been by about 3 degrees Kelvin. Now, you've heard them say, was there a source of contamination? They, in fact, tested whether heat from New York City was affecting their results. It was not. They even expelled the pigeons nesting in the antenna. But the background radiation persisted, as did they. So sharing their puzzlement with others, they learned that astrophysicists at Princeton University had predicted that if there had been a Big Bang, that there would be lingering cosmic microwave background radiation from it. So Doctors Penzias and Wilson had discovered the first experimental evidence that supported the Big Bang theory of the origin of the universe, a truly serendipitous discovery in which perseverance played a big part. But sometimes considerable personal courage is required to pursue an explanation for anomalous data. In the realm of nanoscience and materials, it was long thought that crystals occurred only in periodic patterns that repeated themselves in 3 dimensions. The discovery by Dr. Dan Sheckman of the Technion of an ordered structure without translational symmetry met with such resistance in the scientific community that he was asked to leave his laboratory group. But he would not back down from his findings, and as a result discovered a new kind of phenomenon in nature, quasi-crystals or quasi-periodic structures, structures that in fact had appeared in medieval Islamic mosaics and that had displayed the golden ratio, a mathematical constant that relates to the Fibonacci sequence in which each succeeding number, as you know, is the sum of the prior 2 numbers. Now, the golden ratio also appears elsewhere in art, including in masterpiece paintings. So in fact, at my university, we've undertaken an initiative called ArtX at Rensselaer to teach our students the art in and of science and the science in and of art. Now, neuroscience had a similar prohibition. It was long taken as an article of faith that the formation of new neurons ceases before adulthood in mammals. But thanks to the courage of certain scientists willing to question conventional wisdom and to admit when more neurons appeared under the microscope than were expected, there's been a refutation of that idea. But scientists do continue to look for new methods to settle the question of adult neurogenesis in humans. And in the last 2 months, 2 studies were published, one of which found evidence of adult neurogenesis in the human hippocampus, and another that did not. Now, it is known, for example, that multipotent adult neural stem cells can give rise to the adult primary cells of the nervous system. More specifically, the biomolecular cues that comprise the extracellular matrix can drive the differentiation of neural stem cells into neurons, the basis of neurogenesis. And at Rensselaer, our researchers, in fact, are manipulating these biomolecular cues to enhance neurogenesis in vitro, which can lead to in vivo studies. And in fact, in collaboration with colleagues at Rockefeller University, our faculty are performing neuromodulation using magnetic fields to control gene expression within various neurodegenerative disease models. So out of the struggle to answer the fundamental question of whether new neurons continue to form into adulthood in humans has come a new appreciation for the complexity and plasticity of our unique nervous system, and new hope that we will devise better therapeutics to address injuries and neurodegenerative diseases, whether through neuromodulation, through targeted pharmaceuticals, or even by harnessing nervous system interactions with the microbiome and the immune system. Now, it is often assumed by those outside the scientific community that progress always flows downstream, that it is the discovery of fundamental principles that leads to new technologies. Now, indeed, basic physics understanding at both the smallest and largest scales undergirds astonishing technologies that allow us to address great challenges. An example is the Global Positioning System, GPS, that, as you know, uses satellite-based and ground-based atomic clocks for position and time determinations. And in order to have accurate GPS determinations, both special relativity and general relativity must account for time dilation and gravitational effects, both of which create frequency shifts in the atomic clocks. But sometimes new technologies have to be invented to enable the pursuit of science itself. The exquisite precision of the LIGO detectors, which were designed to register a compression or stretching of space-time 1,000th the size of a proton, while tuning out all vibrations endemic to life on Earth, required advances in many technologies, including lasers, optics, vacuum technology, and even software algorithm development. That's why it took 40 years. More recently, major advances in computation and connectivity certainly have driven science, allowing for the genomic revolution, for example. But science also drives innovations in computation and related technologies. An example, of course, is the invention of the World Wide Web by Sir Tim Berners-Lee in 1989 at CERN, the European Organization for Nuclear Research, to allow information sharing among physicists. So when we consider the structures that support science and engineering, the metaphor of an ecosystem is a very apt one. Complexity theorist W. Brian Arthur has compared the evolution of technology to a coral leaf that builds itself from itself. Curiosity-driven and applied research reinforce each other, as do the investigations undertaken by universities, governments, and industry for very different purposes. Advances in one field seed advances in another. Now, what is important is the unending pursuit of knowledge and all of the ingenuity that flows from it. Now, I had the privilege of serving on the President's Council of Advisors on Science and Technology from 2009 to 2014, which helped the nation at that point to understand both its opportunities and vulnerabilities in science and technology, including in advanced manufacturing, in flu vaccinology, and cybersecurity, among many other arenas. Now, the application of scientific advances, of course, can have vast social consequences. And today, in the so-called Fourth Industrial Revolution, in which the digital, physical, and biological worlds are merging, we have astonishing new avenues of discovery at the largest, the smallest, and the most complex scales. But at the human scale, all of us are leaving our footprints, digital and otherwise, wherever we wander. And innovations designed to connect us, to heal us, and to empower us may also cost us our security, privacy, and even sometimes our sense of our own worth as individuals. And so it is important that scientists are tenacious as well in insisting that our work is applied on the right side of the knife's edge of good or ill, on which scientific discovery and technological innovation always sit. You know, scientific progress and technological innovation as well require all of us, the entire talent pool. And that is why STEM education is so important and why it must be available and encouraged for all of us. We need scientists as well to advise and to be invited to advise policymakers and to do everything possible to help the public at large overcome its fears about too much change too fast, and to understand why it is so important to preserve and expand the ecosystem that generates fundamental knowledge. The World Science Festival is a critical part of that ecosystem. So as we probe dark energy, dark matter, and the origin of our universe, or the ways that the physical matter of our brains give rise to consciousness, or the startling properties of materials and structures considered at the level of the atom or molecule, the pursuit of science enables our lives, but it ennobles our lives, enriches our culture, educates the next generation, and allows humanity to stretch in both its intellectual capacity and, of course, in the array of tools we can use to uplift lives and change the world. So I'm very honored and proud to be here today at this great celebration of science, and I congratulate in advance those remarkable people who will shortly be awarded Kavli Prizes for their groundbreaking work. It is nice to be present once again. Thank you very much.
So thank you for that inspirational keynote address. We have a few minutes before we go to Norway, have a little bit of a conversation. You know, you spoke of the LIGO discovery. Yes. and how many years that took. Can you speak to the funding that required and the foresight it took on the part of the National Science Foundation to continue with the project that wasn't actually revealing much for the first 30, 40 years of research?
Well, part of the reason I used it, you know, it was obviously at MIT, but is that it took foresight at the personal level. And I feel very strongly that Ray Weiss and others represented that. It took foresight at the institutional level, because MIT had to believe in Ray, to give him tenure, and to allow him to pursue those investigations for so long. And of course, the $1 billion that the National Science Foundation committed, and over many years, is something that is very telling about what it really takes to nurture talent and to have the kind of discoveries and innovations that I spoke of in my remarks.
So just wondering, and this is conjectural, of course, but if that project was starting today, what do you think would happen?
Now, you know that's a loaded question, but I think it would be a heavy lift, but I would like to believe that at least some in the Congress would be believers in the need to sponsor such work. Now, I'm one who believes in the pursuit of science for the pursuit of science, because for the reasons I mentioned. But I think it's also important to link what comes out of science and scientific discovery, even if we don't know what ultimately might result, but to even do the backward look to help to animate people's imaginations, but also to have them understand how important this is to our progress, our health, our safety, our economic progress. And I think sometimes that's what we really have to spend time doing in order to bring the message to a point that makes what we do more believable and directly more important to people who are not scientists themselves.
Now, if we do that backward look, and for instance, take the modern gadgetry that you have on your lap and on your wrist, and we look at the fundamental physics that was required for these breakthroughs. It takes us right back to the 1920s, 1930s, quantum mechanics, and calculations have been done that the transistor, which comes from quantum physics, through the years accounts now for something like 35% of the gross national product. Yes. And I give you a small little footnote on that just because it's all friends in here. I once went to look up where the source is for the 35% of the gross national product. I've been chasing it through, and I find that apparently I'm the source of it. Now look, I've not actually done this calculation, all right? So 35% may be wrong, but you know, it's significant.
It's that order of magnitude.
It's definitely significant. So it's clear that fundamental science really is a driver of the economy.
Yes.
So you spoke about the decreasing budget for fundamental science. So this isn't a difficult equation to hold in mind. Fundamental science allows us to have economic breakthroughs. So what's wrong with us?
Well, we have to get back to the fundamental premise that you do have to know something to do something. And as I said, you have to keep the message simple. You got to know something to do something.
So, you know, so people have been rising to the occasion, and I wonder what your view is. I've been asked this a number of times. So we had a couple of marches for science.
Yes.
And the community was kind of split as to whether or not that was a good thing. There were those who were saying, yes, we need to rise up, and the voice of science needs to be out there in the public sphere. There are others who are saying, don't do that. You're going to politicize science in a way that now it's just another left versus right, red versus blue issue. Where do you come down on that?
Well, I think I don't have a problem with marches for science in the sense that I do think that those who are in science and support it sometimes need that validation of being part of the larger group and to be willing to be public about it. And I think there always is a risk of backlash depending upon who picks up on a message, but one cannot be afraid. I mean, one could have said that about the civil rights era or any movement that is important to our society in the broad way. I also think that there are many in the private sector who actually understand and the role of fundamental science in what they do. And because of that, there is support in that frame. Now, I happen not to think that it will substitute for a government undergirding support for scientific research and applied research. But nonetheless, I've always believed that it is a partnership of government, academia, and the private sector that really helps us to move ahead. And that's why, I mean, we're here this morning, and I'm not saying it because we happen to be here for that, but the Kavli Prizes speak for themselves in that regard, and it came out of the creation of a man who made a personal fortune in business. And so we shouldn't forget all of that. And so that's why I was honored to be able to come here today.
And thank you for coming. Along those lines, there is a movement afoot to have a more formalized way that wealthy individuals can give back to the scientific community. I know there's the Science Philanthropy Alliance has come together. So do you see that, 10, maybe less years from now, there's going to be a shift in the center of gravity of the science funding? Is it going to come largely from the private sector?
It could, but I still think that we have to understand that basic research and support for it is a broad public good. And as such, government has a responsibility to support it. But then I think the private sector has the unique opportunity to be at the leading edge in terms of great ideas. And the Kavli Prize is a great idea. I know you thought I was going to talk about a specific scientific discovery, but the Kavli Prize itself is a great idea. And, at Rensselaer, we get to do unique things, and I've spent the greater part of almost 20 years helping the university live through and live up to its great legacy. And one of our greatest benefactors was a co-founder of NVIDIA. And that's because he developed the original graphics processor on which the company was founded. And so that kind of truly virtuous circle is important. But what we do also depends on support for research and for our students that comes from governmental sources.
So we just have a couple more minutes, but having been a university president for some time, do you see a trend or a change in the culture, both broadly defined, but also as it relates to science and the role that has in people's lives and their education?
Well, the irony is that people every day are using what comes out of science, whether it's to play, to work, to communicate. But what some of the great developments, particularly those that relate to communication, to data, and so on, have brought are two challenges. One challenge has to do with bringing forward the fact that science always sits on this knife edge I talked about, where things can be used for good or ill. But it's brought about another kind of challenge, which has to do with this cacophony of voices. And so the question becomes, there's less, weight given to any given voice, including the voice of science. But that's why it's important to take a moment and to talk these things through and to give focus to it and to bring young people and then those who may not even become scientists into the fold.
So sort of one other question, maybe it's you don't have a sort of maybe distinct perspective, but maybe you share it, I don't know. So that's at the university level. At the secondary level,
Right.
Do you think that we should require every kid to go through the same kind of scientific education at, say, the junior high school and the high school level? Not to bias your answer, but should we drag kids through certain areas of understanding that they're never going to use and they don't really need? Is it vital that they have that exposure, or might there be a better way to get them to think in rigorous analytic terms rather than pulling them through a cookie-cutter approach to science education? Not that I have a view on this at all here, but I'm just wondering what your view is.
I think you have to make a bit of a separation. I think cookie-cutter approaches of any kind are not particularly useful. Dragging people, so to speak, is not particularly helpful. But one can invite and excite and motivate and support young people to develop their curiosity and to learn some fundamentals in science and math. And part of the difficulty we have is we do these separated and what we think are separable discussions about science versus non-science and the language or liberal arts and the non. And that's, to me, silly and incorrect, because the two come together everywhere we looked. And that's why I used, as a particular example, I wanted to show tenacity and courage in talking about Dan Shechtman. But I also wanted to show its linkage to art and artistic work and history.
Fantastic. Well, it was great talking to you. Thank you so much for being here today.
My pleasure.
Please join me in thanking Dr. Jackson. Thank you. All right, so I'm waiting for the signal in my ear, but I think we're about 10 seconds away. Is that right?
Hello and welcome to Oslo. It is blisteringly hot here and we are celebrating today the finest scientific minds and the best science in the world. Hello also to our friends around the world, especially those at the World Science Fair in New York. Now this is the 6th Kavli Awards, awarded every 2 years since 2008. The Kavli Prizes are a collaboration between the Kavli Foundation, the Norwegian Academy of Science and Letters, where we're standing right now, and the Norwegian government. And here's a quick message from the Norwegian Minister of Science and Higher Education.
On behalf of the Norwegian government, I would like to congratulate the Kavli Prize laureates for 2018. The Kavli Prize is a prestigious prize, and the Norwegian government is proud to be one of 3 partners. Interest in the research fields covered by the Kavli Prize has grown the last few years, and it draws attention to how research can help solve global challenges. I believe that the Kavli Prize will be even more important in the future. So once again, congratulations.
Thank you to the Minister. Now we are here at the Academy where the announcement is going to be made in just a few seconds' time. Over many months, international committees of scientists carefully and secretly select who this year's laureates are going to be. And a few hours ago, 7 scientists received that all-important call. Now, the president of the Norwegian Academy of Science and Letters, Ole Søyestad, is about to make the announcement. So let's go and see what he has to say.
Ladies and gentlemen, this is a great day for science and indeed a great day for excellence in science. Welcome to the announcement of the 2018 Kavli Prizes. We are honoring great scientists in 3 categories: for work that has provided us with new tools and new ways of thinking about astrophysics, nanoscience, and neuroscience. In the words of the founder of these prizes, the late Fred Kavli, today we honor the science of the largest, the smallest, and the most complex. Now, let us move on to the announcement themselves. Let us begin with the very smallest, nanoscience. For the invention of CRISPR-Cas9, a precise nanotool for editing DNA, prompting a revolution in biology, agriculture, and medicine, the Norwegian Academy of Science and Letters awards the 2018 Kavli Prize in Nanoscience to EMMANUELLE, CHARPENTIER, Max Planck Institute for Infection Biology, Berlin, Jennifer Doudna, University of California, Berkeley, and Virginijus Šiksnys, Vilnius University. Congratulations to the 3 new Kavli Prize laureates. To elaborate on the choice, please let me introduce the chair of the Nanoscience Committee, Professor Arne Brattås, who is with us today. Arne, if you please.
To change DNA is to alter the underlying code for any living organism. Repairing a defect in the genome of any creature, one would have to remove, change, or insert genetic code at atomically precise locations in DNA. With the advent of the truly revolutionary nanotool, the CRISPR-Cas9, the door to curing hereditary diseases and boosting agriculture creaks open a little further. Until now, genetic engineering was slow, imprecise, and costly. CRISPR-Cas9 enables editing DNA similar to how we can modify a manuscript. The system acts like nanoscissors that cut DNA in incredibly precise ways by targeting a single letter, and this allows the potential correction of disease-causing mutations. It's a tool that works on many organisms, plants, fungi, animals, including humans. There are many advantages to the CRISPR-Cas9. It is simple and quick to use and highly robust. A small RNA molecule is synthesized to encode the location of the DNA sequence to be modified. This attaches to the Cas9 protein to form a complex which binds to the target DNA. Cas9 then opens and cleaves the DNA at exactly the desired location. As the segments reconnect, DNA may be inserted or altered. The breakthrough of CRISPR-Cas9 builds on the discovery and exploration of CRISPR. It's an acronym that stands for Clustered Regularly Interspaced Short Palindromic Repeats, a DNA sequence used by the immune system of bacteria against viral attacks. With their teams, Emmanuelle Charpentier and Jennifer Doudna, and independently, Virginia Shixnis, invented a way to combine and develop CRISPR and Cas9 into a powerful nanotool. Their pioneering work and further great advances by a growing number of researchers continues to unleash the enormous potential of CRISPR-Cas9 in experimental biology. It not only offers tremendous opportunities, but also carries responsibilities and risks that affect all humankind. Profound ethical challenges must be addressed and resolved. CRISPR-Cas9 creates new scientific capabilities for positive innovations. Possible benefits are wide-ranging in scope and value. From a fundamental perspective, it's an ingenious technique for basic research that will enable the detailed study of the genetics of many previously intractable organisms. In terms of applications, CRISPR will be used to develop agriculture with regard to changing crops and livestock, or increasing biodiversity. In medicine, attempts to correct disease-causing mutations have already begun, and soon this will be expanded to grave conditions such as muscular dystrophy, sickle cell anemia, and some forms of blindness and cancer. The CRISPR-Cas nanotool initiates a revolution in genetic engineering with limitless potential benefits and pressing ethical challenges. Rarely has a novel technique presented such an opportunity to radically change almost all branches of the biological sciences.
Thank you, Professor Brattås. And now, from the smallest to the largest, astrophysics. For her combined contributions to observational, theoretical, and laboratory astrochemistry, elucidating the life cycle of interstellar clouds and the formation of stars and planets, the Norwegian Academy of Science and Letters awards the Kavli Prize in Astrophysics for 2018 to Evine van Dieshoek, Leiden University. Many congratulations to the new astrophysics laureate. To elaborate on the choice, please let me introduce the chair of the Astrophysics Committee, Professor Mats Karlsson. Mats, if you please.
We live in a universe where molecules play a key role in the physical processes that lead to the formation of stars, planets, and life. Observing these molecules also allows astronomers to probe cold and obscured interstellar clouds in the Milky Way and other galaxies. Our understanding of cosmic chemistry has been revolutionized by a combination of measurements with new observatories and space telescopes, laboratory experiments, and theoretical studies. Among the researchers who have contributed to this revolution, Irwin van Dishoeck is outstanding. Among the many advances made by van Dishoeck and her collaborators are seminal contributions to our understanding of the formation and destruction of interstellar molecules. Their pioneering work on carbon monoxide has been essential for elucidating the evolution of the cold components of the interstellar medium, from diffuse to dense clouds in the Milky Way, as well as a cold star-forming gas in galaxies across cosmic time. Through laboratory experiments, van Dishoeck's team has advanced a quantitative understanding of the growth and evolution of interstellar ices. This work includes investigations of photoprocessing of ices composed of water, nitrogen, carbon monoxide, and carbon dioxide. Such studies serve as a basis for modeling the effects of photodesorption and processing of astrophysical ice. These are key steps in the evolution of molecular clouds and the subsequent formation of stars, protoplanetary disks, and planets. This work also helps to reveal the chemical evolution of our solar system, where comets and primitive meteoritic materials preserve the composition of the original cloud of gas and dust. Recently, van Dishoeck and colleagues have extended this approach in an effort to connect the chemical composition of the comet 67P, visited by the Rosetta mission, with that of young stellar systems similar to our own. Irwin van Dishoeck has masterfully applied spectroscopic tools across a broad range of wavelengths with a superb exploitation of the most powerful astronomical measurement techniques. She used the Infrared Space Observatory to study molecules previously not accessible by microwave spectroscopy. She used the Herschel Space Observatory to follow the trail of water throughout star formation. And most recently, she used the Atacama Large Millimeter and Submillimeter Array to provide the first view of dust traps in disks around young stars, which put observational constraints on planet formation theories. These examples illustrate the remarkable breadth of her approach to fundamental astronomical problems, embracing cutting-edge observations, physical and chemical theory, and laboratory experiments. Irwin van Dishoeck is leading the transformation of astrochemistry into a growing quantitative discipline.
Thank you, Professor Karlsson. And finally, from the largest to the most complex, neuroscience. For their pioneering work on the molecular and neural mechanisms of hearing, the Norwegian Academy of Science and Letters awards the 2018 Kavli Prize in Neuroscience to James Hudspeth, Rockefeller University, Robert FETTIPLACE, University of Wisconsin, Christine Petit, Collège de France, Pasteur Institute in Paris. Many congratulations to the 3 new neuroscience laureates. To elaborate on the choice, please let me introduce the chair of the Kavli Prize Committee in Neuroscience, Professor Ole Petter Ottersen. Ole Petter, if you please.
As I speak to you now, you are engaging an incredibly sophisticated sense that we sometimes underappreciate, yet is central to our daily lives, hearing. We can hear frequencies from 20 Hz to 20,000, discern the pitch of 1/30th of the difference between 2 piano keys, and detect signals that vibrate over eardrums by 1/1000th of a millimeter. Uniquely among our sensory organs, the ear converts sound, pressure waves in the air, into electrical activity, and in doing so, transforms sound into signals that the brain can record and that we can grasp as speech, enjoy as music, or disregard as noise. The 3 Kavli Prize neuroscience laureates have used complementary approaches to unravel the mechanisms by which the inner ear processes sound via sensory receptors called hair cells. James Hudspeth has provided the major framework for our understanding of the transduction of sound into neural signals. Extending from each hair cell is a bundle of fine protrusions that act as sensors. Hudspeth used ingenious methods to reveal how sound-induced vibrations evoke an electrical response in the hair cells via a direct mechanical connection between the hair bundle and ion channels. Critical to hearing, his work also revealed how sound signals, which can be very weak, are strongly amplified within the inner ear. Robert FETTIPLACE has made fundamental contributions to our understanding of sound transduction and demonstrated that each hair cell is sensitive to a specific range of sound frequencies. His experiments reveal that hair cells are organized in a pattern that reflects their frequency selectivity. Using sensitive physiological measurements and theoretical modeling, he discovered that this selectivity reflects an intrinsic electrical property of the cell. This is set by the density and kinetics of its ion channels and induces a resonance at a particular frequency. Christine Petit has explored the genetics of hereditary deafness in humans and identified more than 20 genes that are required for hearing and inner ear development. She elucidated the mechanisms through which these mutations cause hearing defects, thus illuminating the unique biology of hair cells. In the clinic, her work has helped improve deafness diagnosis and subsequent counseling. Several of the genes she identified form major components of the hair cell machinery that converts sound to electrical activity. Collectively, the breakthroughs made by this year's Kavli Prizes have unveiled the molecular and cellular mechanisms that underlie hearing and deafness. In doing so, the laureates have shined light on the sense that allows us to hear music and to listen to each other. Their work serves as a sterling example of how concerted efforts across disciplines can revolutionize our understanding of complex neurobiological processes.
Thank you, Professor Ottersen. Congratulations to the 7 new Kavli Prize laureates. They have all made breakthrough discoveries, providing knowledge that has and will have effects far beyond their fields of investigation. Their contributions stand out as truly excellent and will inspire future generations to use their talents in pursuit of knowledge. Our society and our culture are built on scientific discoveries, and it is a privilege to honor those who contribute the best. We look forward to seeing you here in Oslo on September the 4th for the Kavli Prize award ceremony.
So there you go, 7 new Kavli Prize laureates, all celebrating the very best in basic scientific research and its ability to transform our understanding of the universe. Many congratulations to all of them, and I'm sure the celebrations and discussions will continue all around the world for many months to come. But from us in Oslo, this is goodbye.
We are honored this morning to have 3 accomplished scientists who are with us to talk about the extraordinary breakthroughs this year in astrophysics, nanoscience, and neuroscience. I'd like to bring them all up to the stage now. First, Professor Irwin Shapiro is an astrophysicist at Harvard University and was a Kavli judge for the Astrophysics Prize. So please join me in welcoming Professor Irwin Shapiro. Also with us is Professor Laura Greene, a physics professor at Florida State University, a chief scientist at the National High Magnetic Field Laboratory. She's also a Kavli judge in the nanoscience category. Please welcome Professor Laura Greene. And finally with us is Professor Leslie Vosshall, who's a molecular neurobiologist and director of the Kavli Neural Systems Institute at the Rockefeller University. Please welcome Professor Leslie Vosshall.
Wait, do that again.
All right, so before we get into discussion of the significance of the work that was awarded these extraordinary Kavli Prizes, we have a couple clips. We'll do them one by one. That'll give some sense of the work that was awarded these prizes. So let's begin with the Kavli Prize for astrophysics, which was for the elucidation of the life cycle of interstellar clouds and the formation of stars and planets. So please watch.
Stellar nurseries, the place where stars are born, are some of the most exquisite spectacles in the universe. But the molecules in this dust and gas can also help answer one of the most significant questions of all time. By investigating these marvels deep in space, one scientist has brought us closer to understanding the origins of life here on Earth. The 2018 Kavli Prize in Astrophysics is awarded to Avina van Dieshoek for her pioneering contributions to the field of astrochemistry.
Professor van Dieshoek has made many contributions in the field of what's called astrochemistry, and this is understanding the chemical processes and reactions that take place in the universe.
Trained as a chemist, a chance meeting with a professor of astronomy while on a camping holiday led van Dieshoek to look to the stars in her research.
Professor van Dieshoek has been working in this field for 25 years. When she started, it wasn't understood how important and widespread molecules were, and was really considered not really central to astronomy.
Using her understanding of chemistry, van Dieshoek discovered that the regions where stars and planets form are rich in many kinds of molecules.
This study of molecules where planets are forming is so exciting because we have this vision that one day that we'll be able to find molecules in these young planets that are necessary for the formation of life.
Van Dieshoek's determination has led her to become the world leader in astrochemistry.
She's an inspiration to generations of young scientists, and in particular, a role model for young women entering astronomy. Many scientists become famous for a singular, very important breakthrough. The thing that's so impressive about Professor van Dieshoek's work is she's made so many advances that this has really transformed astronomy.
So Irwin, we're pleased to have you help us think through this work and this award. So you're one of the judges on this committee, so the podium is yours.
The present winner of the Astrophysics Kavli Prize has, if I may use an analogy, or rather a term from football, has been a triple threat. She's not only good at theory, she's also good at observation, and she's also good at data analysis. So she's a triple threat rather than in football for her running, passing, and kicking. Now, if one considers what she also is very good at, namely in scientific organization and in administration, then you clearly get the unprecedented quadruple threat. All right, well, I thought it was funny, but I guess not. Avine, as you already know, got her start in chemistry, and then for her graduate work, she, excuse me, she was under the tutelage of Alex Dalgarno, who was clearly the premier theoretician of atomic and molecular astrophysics in the world. And that was when I first met her in the early 1980s. To digress just a little on the state of astrochemistry at the time, by the late 1940s, there were only a couple of molecules known in interstellar space, and they were two-atom molecules, like carbene, which CH, and cyanide. We don't have to deal with that close up, CN. And then it wasn't until 1970, well, I'm sorry, let me go through the 60s. Then it was, I'm screwing up here badly, sorry. In the 1950s, early 1950s, hydrogen was first discovered in interstellar space, actually at Harvard. And then in the 1960s, several more molecules were discovered, and then in 1970, CO, carbon monoxide, which is still recognized as the second only to hydrogen most common molecule in interstellar space. Now there are, of course, over 200 molecules known in interstellar space. And it was recognized soon after the 1970s that interstellar molecules collected in giant molecular clouds, which were the birthplaces, if you will, of stars. And that was a profound realization. Back to Irvine and her, or Vina, I think she's called, but I've always called her Irvine. She's never corrected me, so I don't know. Anyway, she made her first big contribution in 1988 with John Black when she studied the dissociation rates of carbon monoxide when illuminated, as it is in interstellar space, by ultraviolet radiation. And she investigated not only ordinary CO, but all its isotopic variants, and also investigated the effects of temperature and cloud thickness on the abundances of CO. And this paper, which I said published 30 years ago, is still widely referenced even today. Then, when space observations became available with ISO and Herschel and the US Spitzer, which is the one not mentioned earlier today, she made use of their spectroscopic properties to make a lot of very important contributions, of which I'll mention only one: the freezing out of gas on dust, especially the water molecule, and the insights that gave us into the formation of the early stages of formation of stars. Then she's also been involved in laboratory work. She's now the head of the laboratory in Leiden, where they do experiments imitating what we think goes on in outer space, so that we can vary the conditions as you can do in a controlled laboratory experiment, but you can't do in space. And this gives us very good complementary information to the observations and checking against observations in space. Irvine has been a ball of fire and continues to be a ball of fire all her life. She's published almost 500 refereed papers, and she's not finished yet. She's not even 63. She won't be 63 for 2 whole weeks. And then she's mentored over 42 graduate students and over 30 postdoctoral fellows, so she keeps active. In addition, she's taken on many administrative responsibilities, of which I will mention only one, namely, she was the chair and a member of the Science Advisory Committee for the Atacama Large Millimeter Submillimeter Array in northern Chile, which is now a major ground-based, if not the major ground-based astronomical observatory in the world. And she's even using it for science now that it's operating, and she, with others, made the first clear images of dust traps, which are largely believed to be the birthplaces of planets and comets. So she's still very active. And as I will say, in my humble opinion and that of our committee, she was very deserving of the prestigious Kavli Prize in Astrophysics for 2018. Thank you.
So thank you, Irwin. You know, Tracy Day and I first met Fred Kavli when we were spending a semester at the Kavli Institute in Santa Barbara. And then that was 2003. In 2005, we met again and in New York, and he began to tell us about the prize. We began to tell him about our plans for the festival and how we were thinking about, you know, rough organizational schemes, talking about things in the universe that are very small, in the quantum realm, things that are very big, cosmology, things that are complex, the brain, and he sort of loved this organizational scheme and said it tied in exactly with this prize that he was planning to launch. And this is when it became clear to us that it was a sort of perfect marriage, that this should be the home for where the prizes are announced. So we've just heard about the big. Now, if we move down to the small, down to the nano world, we heard that the prize was awarded for CRISPR-Cas9, which of course is a nano tool for editing DNA, but of course it has a big, powerful impact. And to get a sense for what that tool is, let's look at a quick video clip and then we'll hear some remarks.
From its potential to treat cancer and edit out disease-causing mutations in embryos, to its ability to revolutionize food production and even revive extinct mammals, the broad applications of CRISPR are staggering.
CRISPR is often referred to as one of the most significant breakthroughs of this century, and arguably the last 50 years or so.
The winners of the 2018 Kavli Prize in Nanoscience are Jennifer Doudna, Emmanuelle Charpentier, and Virginijus Šiksnis for their pioneering work on CRISPR-Cas9.
CRISPR-Cas9 can be explained as a Swiss Army knife that allows to repair genes.
Cas9 can be used to correct mutations in human DNA that cause genetic disease.
It means that laboratories don't have to have a lot of money. I think CRISPR is democratizing technology.
Jennifer Doudna and Emmanuelle Charpentier first met at a conference in Puerto Rico.
You had this beautiful example of a serendipitous meeting between two scientists who went back to their respective places of employment, Jennifer in Berkeley, Emmanuelle in Sweden, but continued to foster this cross-continental partnership.
Doudna and Charpentier wanted to understand how Cas9 naturally recognizes and cleaves DNA in microorganisms. They proposed that this mechanism could also be used as a tool to edit DNA in other types of cells, including human cells.
It was a fledgling field. It felt like a bit of a gamble to work on something that didn't seem to have a lot of interest, but it was also this big open territory to make new discoveries.
While Doudna and Charpentier took part in this exciting cross-continental collaboration, a team of scientists in Lithuania were also making headway to understand CRISPR.
Virginijus Šiksnis is a name that I think deserves to be mentioned a lot more when it comes to our understanding of how CRISPR immune systems work, but also having really reached this understanding of how Cas9 works as an enzyme right around the same time as Jennifer and Emmanuelle's research team.
It was really an eureka moment, and we were all very excited about that.
Many scientists believe this new technology should be used with caution, particularly when it comes to making genetic changes that would propagate to future generations. Despite these concerns, the positive impact that Doudna, Charpentier, and Šiksnis' invention could have on the world is irrefutable.
My ultimate wish would be that it could be used to treat serious human genetic disorders.
The possibilities for using CRISPR in different ways feels limitless.
The thing that's amazing is that there's always more to be discovered.
And to give us further insight into this prize, we have with us Professor Laura Greene, who's one of the judges for the 2018 Prize in Nanoscience. Podium is yours.
Oh, thank you very much. It's really a pleasure to be here. It's very exciting and to have a winner here. I am having trouble following such a great speech before me, but I'll do the best I can. The Kavli Nanoscience Laureates, Emmanuelle Charpentier from the Max Planck Society, Jennifer Doudna of the University of California at Berkeley, and Virginia Sickness of Vilnius University are recognized for their invention of CRISPR-Cas9. This is a breakthrough nanotool, and its capabilities for positive innovations will really cause revolutions in many, many fields, including medicine, biology, and agriculture. It will also greatly enhance our understanding of genetic mechanisms. This is the important question. How would you fix a defect in a genome of an organism? The answer is to actually get into the DNA sequence at the exact location where the defect is, and then repair it. The defect may have to be removed, or changed, or even have a different genetic code inserted. You've got to fix it somehow. And that is exactly what CRISPR-Cas9 does. Now, there did exist other methods of editing genes, but they were difficult to use, expensive, and they didn't have the precision that's required. And in fact, CRISPR-Cas9 is built on the earlier CRISPR, which it means clustered, regularly interspaced, short, palindromic repeats. CRISPR-Cas9 built on this, making gene editing simple, easy to use, and inexpensive. Here's basically how it works. A small RNA molecule is synthesized in the laboratory, and this is to encode the exact address of a DNA sequence that you want to target and repair. The next step is the synthesized RNA molecule is attached to the Cas9 protein, and that's the breakthrough. The CRISPR-Cas9 complex is created. This synthesized RNA in this complex then finds the exact place that it was programmed to find, encoded to find in the DNA. Grabs it, it addresses it, and then the Cas9 comes in like a little knife and slices it right there. While the DNA is repairing itself and coming together, what can be done by the biologist in the laboratory is just you remove some pieces, or you can add other genetic code, or you can repair genetic code. And so this allows really precise, cheap, and constructive changing of the DNA code. It works on many organisms, plants, fungi, animals, and humans. So potential applications are incredibly broad-ranging. We envision editing agriculture and livestock and maybe other animals and humans to improve different aspects of health, and also to cure certain diseases. Certain diseases that look extremely promising are muscular dystrophy, sickle cell anemia, and some forms of blindness and cancer. This pioneering research has seen impressive further advances by a large, growing number of researchers all over the world. It's always written up in all the magazines, etc. So it's worth pointing out right here that this is extremely powerful, and there will be ethical challenges associated with CRISPR-Cas9. And it's important, and it was brought up in our announcement, that the community keep discussing this, and this becomes a living document on what the ethical challenges are in CRISPR-Cas9. We salute the brilliance of our Kavli Nanoscience Laureates, Emmanuelle Charpentier, Jennifer Doudna, and Virginia Sickness for inventing this nanotool, which is a complete revolution in genetic engineering and is changing our world. Thank you.
So before moving on, just because I see we have a few minutes, and I'm kind of curious. So, is there a target length of DNA that you cut out? Is it arbitrarily long? Is it?
Well, you cut it at one point or 2 points, and what happens? You make this little RNA molecule, synthesize it in the laboratory, and there's more experts on this than I am. But that has the exact genetic code to go find the exact point on the DNA molecule. So it's like a lock and a key. And there they're disparate. So it finds the right lock and key, finds the exact right sequence, and it's grabbing along this Cas9 protein. And then this Cas9 protein goes, okay, I'm here now, and my job is to cut. And it cuts. And then there's other synthesis techniques where the biologist can go in there and say, okay, we just cut these two places and it heals, okay? Or you can say, we just cut these two places and we're inserting a brand new piece of DNA in here. And it's boundless, the opportunities and the challenges and how powerful it is that you can basically, any of us can actually buy one of these things and work on it in our basement. So.
And if I may add just a word.
Please.
I asked Jennifer herself this question
okay.
that you asked. Is there any limit to how much you can cut out at once? And she said no.
Huh. Amazing. And if you want to actually know more, I believe there's a program that we have, is it today or later today? Yes, there's a program later today, if anyone is around, that's going to focus on the science, which I know nothing about, but I intend to be there. That's great. All right, so thank you very much. Let's now finally turn to our third realm, the realm of the complex, the prize in neuroscience, awarded to 3 scientists who have shed light on the fundamental processes of hearing and deepened our understanding of deafness. So we have one more clip to give us some insight into that.
Hearing is critical, yet it is often taken for granted. This important sense allows us to respond to sound in our environment, keeping us safe from danger. It's also crucial for communicating with spoken language and appreciating music. The winners of the 2018 Kavli Prize in Neuroscience are James Hudspeth, Robert FETTIPLACE, and Christine Petit for their groundbreaking research unraveling the mysteries of how we hear.
These 3 scientists have taken really novel methodological approaches to hearing that include very sophisticated biophysics and cutting-edge human genetics to unravel the cellular and the molecular mechanisms that enable those hair cells to transform sound into electrical impulses in the brain. I think from this work, we understand how precious these hair cells are. If a hair cell gets damaged, their ability to transform sound into those electrical impulses is blocked, and that results in profound losses of hearing or even complete deafness.
James Hudspeth discovered that these sensory receptors in our ears actively twitch, creating a built-in amplifier system.
James Hudspeth has performed these amazing biophysical experiments where he found that the movement of the hair bundles relative to one another creates a mechanical force that actually pops open the channels that let potassium ion flow into the cell. And that's what initiates the electrical signal. That's the foundation of hearing itself.
Meanwhile, Christine Petit took a very different approach to understanding hearing. Petit worked with doctors in places like Syria and Jordan, where profound deafness is prevalent in large families.
She's focused on families with congenital hereditary deafness with a very early onset. By studying the genes that have been altered in those families, she's actually identified almost 24 different genes that are required for normal hearing. And amazingly, all but one of those genes is actually needed in the hair cells themselves.
Robert FETTIPLACE was one of the first people to record hair cells in the inner ear. He found they are individually tuned to different frequencies of sound.
Robert FETTIPLACE found that cells that detect different frequencies are distributed in different positions through the spiral of the inner ear.
Hudspeth, FETTIPLACE, and Petit's innovative research is significant. It has the potential to benefit the 5% of the world's population who suffer from disabling hearing loss.
And we're thrilled to have Professor Leslie Vosshall here, who will give us further insights into this prize.
So it's my great pleasure. Of the 7 Kavli laureates, we have a living, live laureate in the audience. So my beloved colleague, Jim Hudspeth, is here under the veil of secrecy. Also his spouse, Dr. Maureen Packard, who accompanied him, and a few colleagues. I had to lie to them to get them here because, of course, it's a closely guarded secret. Most people didn't find out until the presentation. So what's the importance of the discovery of the 3 laureates? Well, we lived it. We lived it when the live feed from Oslo didn't have sound. So we temporarily all experienced congenital deafness. We also experienced the cocktail party effect when there was audio coming faintly from the speakers on different parts of the room. We also...
All by design. All by
exactly.
design.
And then the high intensity sound and then the extremely low intensity sound. And we also experienced lip reading, right? So I think it was brilliantly orchestrated.
Thank you.
So
Thank
what
you
is
very
hearing for? So it's, of course...
synchronized with the sound.
Hearing is for danger, for love, and for beauty. So we use it as predator and prey to listen to each other. For love, of course, social behavior, listening to our spouses and our children. And for beauty, for music. And what's amazing about the sense of smell is we also encode similar sounds, have different meanings. So the burbling brook is pretty, but the torrent of a flash flood is scary. The sound of a fireplace is homey, but the sound of a forest fire is terrifying. And so what's amazing about the auditory system is that it's incredibly sensitive. And it does decline with age. So after the age of 40, all of us will begin to decline in our capacity to hear.
What did you say?
And about half of us over the age of 80, except for Eric Handel, have severe hearing disorders. And my favorite story is that teenagers have developed a special ringtone for their cell phones that is inaudible to anybody over the age of 40. So how do we understand how the sense of hearing works? It's an incredibly difficult problem to crack biologically because there's very, very few cells relative to other sensory systems. So by orders of magnitude, fewer neurons, cells that are responsible for sensing auditory signals. They're encased in these nearly impenetrable organs, which are resistant to recording and to biochemistry. And they're exquisitely sensitive to sound. So some of the biophysics, of course, has to be done in soundproof bunkers. So what are the unique contributions of our 3 laureates? So you already heard some of this, but Christine Petit had this beautiful genetic approach where she went in and systematically tried to map the genes for human deafness. This was a heroic and a brave approach. It wasn't immediately clear a priori that this would work, that you would be able to have single genetic defects that were mappable. And so she systematically defined not only how the auditory system develops, how it wires, and then the biomechanics and biophysics of how it functions. So these were enormously important contributions. Robert FETTIPLACE was one of the first people to record the electrical activity of these hair cells. And again, because it's so difficult to access them, a lot of people in the trade work with exotic creatures like frogs and lizards and other amphibians, where the preparation is slightly more accessible. And he, of course, discovered that the way you encode different frequencies in the hair cells is to tune them using the concentration of different ion channels to have cells that are tuned to low frequencies and high frequencies. And then finally, my beloved colleague, Jim Hudspeth, made fundamental discoveries about how mechanical movement actually activates the hair bundle. So using a combination of biophysics, computation, and neurophysiology, figured out that just deflecting the hair bundle pops open via a tip link directly ion channels that actually activate these cells. He also discovered the amplifier, so the way that we are able to have incredible sensitivity across low intensity and high intensity is that the ear itself has a mechanism to bring up the volume so that we can hear low sensitivity sounds. And then finally, those of us who are losing our hearing, he has been working beautifully in the zebrafish to discover how hair cells form and how it's possible to regenerate them so that one day I can hear my daughter's cell phone ring. And so with this, I really want to congratulate Jim. He's a giant in the field of sensory neuroscience, and I'm so pleased that we can celebrate with you today.
So, I do not mean to put you on the spot, and if you're not up for this, please say so. But do you want to say a few words as long as he's here? Fantastic. Professor James Hudspeth, 2018 Kavli Prize winner in neuroscience.
Thank you. I don't have very much to say. First and foremost, like everybody else, I would like to go home. So we'll get this over with. But this is an opportunity to say one thing that I think hasn't been said. I thought Dr. Jackson's talk was very clear and gave this interesting metaphor of the scientific endeavor as like a coral reef, something that regenerates itself. But coral reefs can be bleached, and that's happening right now. In our society, science is suffering the same thing, and we're foolish if we don't take that seriously. Now, this group of people, this is a matter of preaching to the choir, right? We all know the importance of science. Most of us are involved in science. We don't need to say more about it. But we do need to get the word out, and I think that we scientists have to do that work, and I think we've done a very, very poor job of it. Obviously, an effort is being made through the World Science Festival to better publicize what science is about. But I think we are partly missing the boat, and here's how. I spoke last year at the University of Chicago to a lay audience, a lot of high school students. It was very fun. I mean, I do that here and do it elsewhere. But it's interesting to talk to these people and to be reminded of why we do science. I'm not in it for the money. You're not in it for the money, Eric? No. None of us is. What attracts us to science in the first place is something, a dark, shabby secret we don't ever talk about. It's the aesthetics. I mean, it's the beauty of science that brings us to it. It's not technology, it's not medical, it's not any of this stuff. As kids, as young scientists, what attracts us is the beauty of it all. That's what got me hooked on this particular system. We don't communicate that. It's not out there. Even science festivals and the like tend to focus more on applications. The applications are important. We need to keep doing that. And that will, in a way, take care of itself. But the issue arose, should the government be paying for basic research? A case can be made that that isn't a necessity. The Italian government did not pay for the Renaissance. The Medici did, right? It's the princes. So we were talking about the rich, the wealthy, who can make contributions to pay back to society. And science ought to be considered, I mean, by science I mean the disinterested pursuit of the understanding of the nature of things, period. That kind of science ought to be supported by people who want to see it as an accomplishment of society. It's no different from art. And it, I think, should be viewed that way and communicated to that way. To young people in particular, they recognize that. And I think we're a little bit shy about talking about the real beauty in science. And I think we need to have regular lectures in a non-university venue, town hall, when somebody will pay me for it, once a month, have scientists who come and talk about why they do science, what's beautiful about it, and why people should appreciate it the same way they should appreciate the Metropolitan Museum of Art. That's my commercial. Thank you very much.
Thank you. So thank you. Thank you very much. And just so you know, we share that philosophy with you completely, that it is the beauty, it is the wonder, it's the aesthetic of science that drives us all forward. And indeed, we do tend to focus on applications in the world at large. But part of what we do at the festival, and we need to do it more for the public at large, is to show kids, to show adults why it is we do what we do, to show them that it's the beauty, it's the harmony, it's the richness, it's the wonder of the world, the way it can all come together in a few elegant mathematical equations that can tell us details about the universe at its first few seconds, all the way toward the very end of time, give us insight to the edge of a black hole, to the inners of the working of the human mind. This is really what it is all about. So we second that view of science completely. So thank you for articulating it here this morning. All right, that's the end of our program. I just want to give thanks to everybody who participated with us. Dr. Shirley Ann Jackson, again, thank you so much for your inspirational speech. Our panel here as well, Irwin Shapiro, Laura Greene, Leslie Vosshall, thank you so much for your remarks. Thanks, of course, to the Kavli Foundation, a partner of the World Science Festival from the very beginning. Thank you so much. And everybody else, enjoy the rest of the week's programs. We hope to see you out there at the World Science Festival. Thank you very much.
Thank you.